All right, we are on our last lesson for Unit 1, all about limits, and we're going to talk today about continuity and discontinuity. I'm going to do much of these charts with you, but leave some blanks for you to finish as part of your assignment, and then some homework questions as well. So for this first function, we're going to look at the function's value at the at x value of 2, the limit as x approaches 2, because they may not be the same, a bit of a sketch if you've got space for that on your handout, and talk about continuity. So for the first one, I have a cubic. F at x equals x cubed minus x. Oops, sorry. Okay, f at x equals x cubed subtract x. So I have used a graphing software for this thing, and more or less it does a zoop. Okay. We know with this cubic function that it is going to be continuous, and it's going to be defined at f at 2. So if I put a value of 2 into the function, I get 6. The limit for my function, if you trace with your fingers as you approach the value of 2, and my graph is horrendous, so let's fix that a little bit. Worse, perhaps. The limit as we are approaching from the left and from the right is going to approach that same value of 6. This is a continuous function. There are no holes or asymptotes. The limit is the same as the value at that place. For the second one, we have f at 2. If I put a 2 in there, I'm going to have a problem. I'm going to have my calculator swear at me. We could write that. We could write undefined. If I do the limit as the function approaches 2 of my function, I can use my factoring strategy to say that I have x minus 2, x plus 1. Simple trinomial over x subtract 2. I was suspicious with the x subtract 2, that's why I went ahead and factored it. I can get rid of the indeterminate 0 over 0 problem, and then I can do a substitution and I get a value of 3. So this function has a problem when x is 2, but it has a limit as x approaches 2. Let's have a look at that graph. It's going to present like x minus 2. Okay, so I have it presents as x plus 1. F at x equals x squared minus x minus 2 over x minus 2. So there is a hole there that's hard to see on graphic technology, but it does have a limit as you approach from the left and from the right, but it is not defined there, so that can happen as well. So we have our limit, but it's not defined. This is discontinuous at x equals 2. The next one, I want to know the value of that function at f at 2. If I put a value of 2 into that function, I have a problem. It is not defined there. But the limit is a little bit on the trickier side. Let's have a look at the graph for f at x equals 1 over x minus 2 squared. At 2, I have a problem, and it is not a hole, it is an asymptote. This function, however, swoops up from both directions. So it is hard to discuss limits. Is that limit infinity? Or does it never get there? Or possibly no limit? Discontinuous. Okay, we have piecewise. Okay, let's have a look at it for a second. We're looking about x minus 1. So it looks like x squared minus 3 as we travel and include to the left and include negative 1. So let me just fill this in here for a second. X squared minus 1 minus 3, 2, 4. My smartboard's out of alignment. There is that curve with my transformational thinking. X minus 1, so it does that towards the right. This is continuous. It is defined for all of those values. For my value at 2, I can put a 2 in to this section and I get a value of 1 for the function. There is a limit as we approach 2 for that function. I can just put that value in. And let's look at the graph for a second. As we approach 2, we are going to be approaching the same value from the left and from the right. It will be the value of 1 as well. So I am looking at x minus 1, which equals 1. It is continuous. It is continuous everywhere, but certainly continuous there. Okay. The next one, 4 minus x squared if x is less than 2, 3 if x is greater than or equal to 2. Okay. Oh, I can see that. That's good. Okay. So if x is greater than or equal to 2, my function has a value of 3. For values less than 2, I have 4 minus x squared. So 1, 2, 3, 4. Something close to that. So that one is defined at x equals 2. It has a value of 3, but it does not have a limit because the limit would be different coming from, whoops, can't spell either, is different from the left and from the right. So we could write that as the limit as x approaches 2 from the right would have a value of 3. The limit as x approaches 2 from the left would be, put a 2 in there, would be 0. So it is discontinuous at that place, and there is no limit. So we have all those possibilities. This one we just are looking for where it is discontinuous. So it is discontinuous when x minus 3 equals 0. So it is discontinuous at x equals 3. So for my continuity, it is continuous for x is a real number. X does not equal 3. That is where it's continuous. It looks an awful lot like our domain. This function is discontinuous where x squared plus x subtract 6 equals 0. And that would tell us where it's continuous by looking at the opposite. Can you and your table partner finish filling out this chart? A graph could be helpful, especially for the third one, and we have some homework questions assigned.